everyone. I'm Huanqi from Tsinghua University, and I'm here to present our work on Mat2Stencil, a modular matrix-based DSL for explicit and implicit matrix-free PDE solvers on structured grid. A long name, right? Our team is mostly background in the high-performance computing, so it might be not so professional from time to time, but bear with me. So first, let me get some background on the PDE solvers, which starts from the stencil DSLs. There are already many of them implementing stencils targeting PDE solvers. In those languages, user can define stencils corresponding to discretized PDEs, which is usually a small weight grid. And applying such stencils onto a grid will get a weighted accumulation on the on each point's neighborhood, like in this equation. We can see that it reads the 5 points around xij and compute the yij. By applying those stencil operators, written down stencil DSL programs can compute the result grid in embarrassingly parallel and encourage no spatial dependence. Those computations serves explicit solvers well, but not for the implicit ones. We denote such computation as Jacobi-style stencil and following the Jacobi iteration algorithm. Unlike explicit solvers, only requiring applying those stencils, implicit schemes, that's a kind of time scheme, when executed on structured grid, they require solving linear systems. So we can see here that in implicit solvers, it needs to solve A applied on X equals B, in which we can see that the application is actually linear. So it becomes a linear system, linear problem to solve. The solving can be achieved through direct methods and iterative methods, both of which will require spatial dependence, like it needs to first solve x minus 1j and then get the xij to be determined. So we notice this kind of stencil operations as pseudo-style since it's still stencils given it operates on the neighborhood, but it has the spatial dependencies that reflect the structure of the Gauss-Seidel iterations and more algorithms. But this kind of stencil operations is not yet addressed by existing stencil DSLs. So another direction looking at the problem is to see the stencils as sparse matrices. It works for both explicit and implicit solvers, in which we can see the 1D case of stencil A applied on X is equivalent to applying a sparse matrix multiplication. And so in this abstraction, the steps taking an implicit solver will be first construct the sparse matrix to be stored in memory like in CSR or ELL format, and then calling the third-party libraries to compute the different sparse linear algebra routines. So we here have two kind of methods here, one being matrix-based and the other being matrix-free. So the matrix-based method is useful in the implicit solvers, but is slow due to lack of structure in the library implementation, and it's hard to program since the matrix construction for complicated problems can be twisted. On the other hand, matrix-free approaches, mostly the stencil DSLs, are fast and easy to programming, but only works for explicit solvers. So the basic idea is to bring matrix-based abstraction to the matrix-free implementations, mostly over DSL. Up to here, we can start introducing our domain-specific language, which is Mat2Stencil, turning matrices into stencils, either in explicit or implicit solver. The first thing to resolve is the matrix construction, in which we identify some basic matrices and enable arithmetic between them that helps constructing complex problems. For example, the dx matrix here is a discretized version of the par 2 par x differential operator here. By using it, the equation below can be discretized easily into either explicit or implicit form. We can see that the first one is simply multiplication between matrix and vector, and the next one is to have requires to solve the linear system. And with this abstraction, we can show an ultimate example that in the NAS Parallel Benchmark, they need to solve 3 of the equations. They took pages to define the scalar form in their tech report, but in our DSL, we can write it down in merely 3 statements. And to describe the structure sparse matrices we mentioned above, we note that structure sparsity can be expressed as codes. In specific, mimicking the compressed sparse row format, which is widely used in the sparse linear algebra routines, we ask for a row function for each sparse matrix that it accepts a row index as a parameter and returns a list of non-zeros in a row, each of which is a pair of column index and matrix value. The example matrix here is just the above example, and it can be implemented as the right set. We can also enable row functions with various additional features. One is to allow it to have row index dependent control flows, and the other is to automatically derive row domain size from the column domain so that it's more general and can be applied to any sized, arbitrarily sized grids. Besides, we also support multidimensional domains and tensor type values for the structure sparse matrix, which we talked in detail in the paper, but we'll omit here. And then it's a comprehensive example here, Gauss-Seidel iteration. It's an example of implementing the Seidel-style routines in our language, and there's more of them, not just this one. But the core idea shares, since they all read and write to vectors according to sparse matrices in domain loops. And finally, M2S support a rich set of operations based on the row function abstraction. It can do iterative solving algorithms through invoking row functions in the domain loops, as just described. And it can also assemble new structured sparse matrices through wrapping row functions into new ones, so that we can multiply, adding, or subtraction between 2 sparse matrices. Thanks to all of that, we can program the various problem solver in about 5 times to 10 times shorter. And the next thing, it comes down to how we stage the code into matrix-free, since we use the type-based multi-stage programming. And it's very much like LMS, but we make it possible to overload the corresponding methods for the classes representing stage 2 symbols, making it customizable. So we then overload the domain objects to get its for loops staged into nested for loops, so that it's not generating the loop body at a compile time various times. And the idea to stage it out is actually splitting it into 2 stages. One is to compile it in Python, and the other is generate the code on FreeTensor. FreeTensor is our also a work by our co-author. So The staging process goes smoothly, except on this important and common pattern. Consider the code here. It manipulates stage 1 object non-zeros. And with regard to the stage 2 condition, I larger than 0, recalling that I is a stage 2 iteration variable. For such programs, human solution would to be discussed different cases, either I larger than 0 or not. So our solution follows. Whenever a condition failed to resolve it at compile time, we backtrack and discuss both possibility. The backtracking is accomplished through throwing an exception containing the condition expression, and then the domain loop handler, which is the overloaded for each method, it catches the exception, try twice, one assuming it's false and the other true, and finally wrap everything together into an if-then-else statement. Additionally, identifying the commonly overlapped condition expressions, we perform deduplication with the help of C3 so that the cases number won't explode. Finally, is our backend. It mainly involves our novel automatic parallelization method Sooth, which is based on the polyhedral dependence analysis and our newly came up strategy. So the point is that unlike the embarrassingly parallel Jacobi-style stencils, Seidel-style stencils are harder to parallelize. They have spatial dependence inside their nested loops. In this example, the written cell of X depends on the first, needs to be computed after the first terms on the right-hand side and must be earlier than the later four. So existing autoparallelism methods suffer from either high startup cost or bad locality. So we want to resolve this issue. Firstly, we retrieve the dependence graph from polyhedral analysis. This is expanded and actually is in symbolic form. Then we check the dependencies crossing the thread boundaries, in which the thread's tile size is determined by the grid size and thread number. And then notice the, I don't know if you can see that clear, but it's there's a red arrow here, and we can see that the three blue arrows dominate this one. So the red one is redundant, and we want to eliminate it. And eliminating such synchronizations, we get a compact set of synchronization to work with, and then we can do code generation on the result. So the whole thing is automatically analyzed and generated to the code which is parallelized with OpenMP. And as a result, our system is able to run on a commodity server, a single commodity server with comparable performance to the manually optimized implementation. So that's all. Thank you.
Okay, step up with questions, please. I was curious if you're familiar with Phoenix.
I'm sorry?
Phoenix, which is a language that takes Python-like code and then compiles it down to finite element and finite volume solvers for PDEs. And how would you relate your work to that? Would this be another backend, possibly, for Phoenix?
I don't really heard about it.
Okay.
I'm sorry.
And then, okay, a related question to that is, what surface language would you imagine a programmer would use for interacting with Mat2Stencil? Is the language that you showed the surface language, or would you imagine compiling down from something else to that?
Our front-end language is embedded in Python, and we compile down to first free tensor IR, and then it's down to C, and gets compiled by GCC. So.
Okay, excellent.
Thank you.
Other questions? And let's thank the speaker.